Is this where... Ah, there we go. Well, welcome to tonight's live stream and video. In tonight's video, we'll be going through core Windows processes, learning a little bit more about the Windows operating system and getting better at understanding what we're dealing with from a defensive perspective, but also from an offensive perspective, because the better we understand the operating systems we're working with, the better we can either defend or exploit them. So tonight we're going to be going through the next Try Hack Me room that is part of the SOC 1 training path, and it's called Core Windows Processes. Now, let me just move my screen a little bit to the side. There we go, so you guys can see that. So tonight we'll be going through this room and we'll be learning a little bit more about Task Manager, the system, smss.exe, CSRSS, WinInit, services, SVC host, LSAS, WinLogon, Explorer, all these different processes that make up the Windows operating system that are core to the operating system. It says explore the core processes within a Windows operating system and understand what normal behavior is. This foundational knowledge will help you identify malicious processes running on an endpoint. I've already started this machine just so that it has enough time to boot up. But let's read the introduction. In this room, we will explore the core processes of a Windows system. This room aims to help you know and understand what normal behavior within a Windows operating system is. This foundational knowledge will help you identify malicious processes running on an endpoint. The Windows operating system is the most used in the world, whether people like it or not, and the majority of its users don't fully understand its interworkings. Users are simply content that it works, like anything complex such as a car. It starts and you can drive from point A to point B. Now regarding computers, if they can surf the web, read/answer emails, shop, listen to music, and watch movies, all is well. It took a long time for users to grasp the need for antivirus programs fully. Only when one of their essential everyday computer functions is disrupted is when antivirus matters. Antivirus was enough over 5 to 7 years ago, rough estimate. Time changes everything. Malware and attacks have evolved, and antivirus is no longer enough. Antivirus has struggled to keep up solely based on how it is designed to catch evil. Today, antivirus is just one solution within the layered defensive approach. New security tools such as EDR, which is endpoint detection and response, have been created because antiviruses cannot catch every malicious binary and process running on the endpoint. In fact, antivirus can't really detect the behaviors of an adversary. So anything, or even the behaviors that a malware sample will perform on an endpoint, things that may look shady, even if it doesn't have the exact signature for that malware, if it doesn't know if it can't detect how it's behaving, then it's not as helpful anymore. But guess what? Even with these new tools, it's still not 100% effective. Attackers can still bypass the defenses running on the endpoint. This is where we come in. Whether you're a security analyst, SOC analyst, detection engineer, or threat hunter, if one of the tools alerts us of a suspicious binary or process, we must investigate and decide on a course of action, knowing the expected behavior of the systems we have to defend. A Windows system. In this case, we can infer if the binary or process is benign or evil. The machine attached to this task will start in a split screen view. In case a VM is not visible, use the blue show split screen view at the top of the page. If you want to access the machine via RDP, these are the credentials. So I got that. Well, let's open that up in split screen view. That's good. Now move this back. Alrighty. So our first port of call is the Task Manager. This is riveting stuff, guys. Task Manager is a built-in GUI-based Windows utility that allows users to see what is running on the Windows system. It also provides information on resource usage, such as how much each process utilizes CPU and memory. When a program is not responding, Task Manager is used to end or kill the process. We'll give a brief overview if you're unfamiliar with Task Manager. To open Task Manager, right-click the taskbar. When the new window appears, select Task Manager. So right-click and Task Manager. If you don't have any explicitly open tab apps, you should see this, which is, it says there are no running apps, which is what we see here. That is not what I wanted to do. Weird, not seeing much, eh? Within a Windows system, many processes are running. Click more details. And we have a better view of what's actually running on this machine. Okay, now we're getting somewhere. Notice the 5 tabs within Task Manager. By default, the current tab is Processes. So we have Processes, Performance, Users, Details, and Services. If you're running Task Manager on your Windows machine, you might see additional tabs. As shown above, you may notice the processes are categorized as follows. We've got apps, background processes, and we scroll down, Windows. There we go. Wait, just went past it. Windows processes. The columns are very minimal. The columns name, status, CPU, and memory are the only ones visible. To view more columns, you simply right-click on any column and you can select. So we can see the process ID there. We can see the process name. We can see the command line. Which is kind of fascinating. That's cool. Never knew you could do that. To view, the view looks a little better. Let's briefly go over each column, excluding name, of course. So we have type. Each process falls into one of 3 categories: apps, background processes, or Windows processes. Publisher. Think of this column as the name of the author of the program. PID. This is known as the process identifier number. Windows assigns a unique process identifier each time a program starts. If the same program has multiple running processes, each will have its unique process identifier, or PID. Process name. This is the file name of the process. In the above image, the file name for Task Manager is taskmrg.exe. So there we go, process name, taskmrg.exe. Command line, the full command used to launch the process. CPU, the amount of CPU the process uses. A note on the command line, this is oftentimes when you're looking at the logs within some sort of seam or anything like that, it will come with this kind of information, the command line, and you'll often see that these processes are launched from this. And memory, the amount of physical working memory utilized by the process. Take a drink. Task Manager is a utility you should be comfortable using, whether you're troubleshooting or performing analysis on the endpoint. Let's move to the Details tab. This view provides some core processes that will be discussed in this room. Sort the PID column so that the PIDs are in ascending order. So there we go. Add some additional columns to see more information about these. Good columns to add an image path name. Select columns. We want image path names, path name, and command line. There you go. Just make this a bit smaller so we can see. These two columns can quickly alert an analyst of any outliers with a given process. In the below image, PID 384 is paired with a process name SVC host, a Windows process. But if the image path name or command line is not what it's expected to be, then we can perform a deeper analysis on the process. So 384, local service, SVC host, and then it's got these extra things. Of course, you can add as many columns as you wish, but adding the columns that would be pertinent to your current task is recommended. Task Manager is a powerful built-in Windows utility, but lacks certain important information when analyzing processes, such as parent process information. It is another key column when identifying outliers. Back to SVC hosts. If the parent process of PID 384 is not services.exe, this will warrant further analysis. To further prove this point, where is services.exe? Based on the above image, the PID for services.exe is 632. But wait, one of the SVC host processes is 384. How did SVC host start before services.exe? Well, it didn't. Task Manager doesn't show a parent-child process for you. That is where other utilities such as Process Hacker and Process Explorer come to the rescue. So we have Process Hacker here and Process Explorer. Moving forward, we'll use Process Hacker and Process Explorer instead of Task Manager to obtain information about each Windows process. As usual, it's encouraged that you inspect and familiarize yourself with all information available within Task Manager. It's a built-in utility that is available in every Windows system. You might find yourself in a situation where you can't bring your tools to the fight and rely on the tools native to the system. Aside from Task Manager, it would be best if you familiarize yourself with the command line equivalent of obtaining information about running processes on a system, task list, get process, or PS, and WMIC. There's a lot to go there. So let's have a look at the next section, looking at system. The first Windows process on the list is system. As mentioned in a previous section, that a PID for any given process is assigned at random. It was mentioned in a previous section that a PID for any given process is assigned at random. But that is not the case for the system process. The PID for system is always 4. What does this process do exactly? The official definition for Windows internal 6th edition is the system process ID 4, is the home for a special kind of thread that runs only in kernel mode, a kernel mode system thread. System threads have all the attributes and context of regular user mode threads, such as hardware context, priority, and so on, but are different in that they run only in kernel mode, executing code loaded in system space, whether that is in nto.skrnl.exe or in any other loaded device driver. In addition, system threads don't have a user process address space and hence must allocate any dynamic storage from operating system memory heaps, such as a page and non-page pool. What is user mode, kernel mode? Visit the following link to understand each of these. have a look at that. User mode and kernel mode. So user mode and kernel mode. A process in a computer running Windows operates in two different modes, user mode and kernel mode. The process switches between these modes depending on the type of code it's executing. Applications operate in user mode, while core operating system components function in kernel mode. Although many drivers operate in kernel mode, some can function in user mode. So diving in a little bit deeper, user mode. When you launch an application in user mode, Windows creates a process for it. This process provides the application with a private virtual address space and a private handle table. Since each application's virtual address space is private, one application can't modify another application's data. Each application runs in isolation, ensuring that if one crashes, it doesn't affect other applications or the operating system. The virtual address space of a user mode application is also limited. A process running in user mode can't access virtual addresses that are reserved for the operating system, limiting the virtual address space of a user mode application prevents the application for modifying or damaging critical operating system data. So basically, user mode is where applications run. That is the space, and it's given virtual address space, which means that it's segregating each application into its own process so that they don't clash into each other. Kernel mode. All code running in kernel mode shares a single virtual address space. As a result, a kernel mode driver isn't isolated from other drivers or the operating system. If a kernel mode driver mistakenly writes to the wrong virtual address, it could compromise data belonging to the operating system or another driver. If a kernel mode driver crashes, it causes the entire operating system to crash, which is not good. The following diagram illustrates the communication between user mode and kernel mode components. Can we make this bigger? Yeah, we can. Yeah. So we have our applications communicating with the Windows API and user mode drivers. Okay, so we've got that there and then that there. Okay, so basically all our applications work in this level, and it abstracts from the kernel, which is like where the operating system functions and what communicates with the hardware. As you can see here, we have the hardware. It's then abstracted to then be able to communicate to the operating system kernel. There are file system drivers and other kernel mode drivers to help communicate hardware to software. And then this then communicates into the user mode. That's basically the difference. Kernel mode deals with how hardware communicates with software at the operating system level and kernel level. User mode is how applications then communicate with the kernel at the user level, where you and I are using things. All right. That is small. That working? That's a bit better. Now, what is normal behavior for this process? Let's use Process Explorer and view the properties of system. So, go in here. Which one do I use? This one? Sure. All right. Okay, so we have system here, PID4. So we right click and let's have a look at the properties. Yep. For path nothing. There is no parent and it's being run by NT Authority System. The information is slightly different if we view the system properties using Process Hacker. So let's move that. system here. Go down to properties. All right, so, geez, I want to see those side by side, but I'm not allowed to. Or maybe. Let's put you right in. All right. So we have the difference is image path here is NTOS kernel. That's the image file name. But here we don't have anything, no file names, parents, nothing. Whereas this has system idle process is the parent. Technically this is correct. You may notice the process actor confirms this is legit because it's verified. Where does it say? Verified, Microsoft Windows, there we go. What is unusual behavior for this process? Parent process, aside from system idle process, multiple instances of system should only be one instance. A different PID, remember the PID will always be 4 and not running in session 0. Where does that say that? System idle process, yeah. I don't think it says it there. T-kernel, yeah. What PID should system always be? And the crowd said 4. All right, moving on, system SMS s.exe. The next process is SMS s.exe, session manager subsystem. This process, also known as the Windows Session Manager, is responsible for creating new sessions. It is the first user mode process started by the kernel. This process starts the kernel and user modes of the Windows subsystem. You can read more about the NT architecture here, which we won't right now. This subsystem includes win32k.sys kernel mode and winsrv.dll user mode and csrss.exe user mode. Session Manager subsystem starts Windows subsystem CSRSS and wininit.exe in session 0, an isolated Windows session for the operating system, and CSRSS and winlogon for session 1, which is the user session. The first child instance creates child instances in new sessions done by smss.exe copying itself into the new session and self-terminating. You can read more about this process here. So let's have a quick look. So we have it here. Session 0. Oh, there we go. We have SMSS. Have a look here. That is not what I wanted. And I just shut that. Interesting. Okay. And okay, so that's what we're doing. We're looking in, is that in Process Hacker? Having a look at the properties in Process Hacker. It should open. Okay, So we have both processes here. You can tell they're different because of the PID at the top. And what we're looking at is the session number, which is under token. Ah, there we go. So we have session 0 and session 1. So the subsystem manager starts Windows subsystem, which is this, and WinInit in session 0. So it's an isolated Windows session for the operating system. Oh, okay. And csrss.exe and WinLogon for session 1, which is the user session. So this is where the operating system sits, and then this is where our session sits, what we can see and everything we can do. Any other subsystem listed in the required value of this registry key is also launched. So we can right click here. Can we do that? No. Have a look in the registry. Hey, how's it going, Devel? So we're going to system. Local machine. System. Current control set. Control. Session manager. And subsystems. This is so slow. Okay, so we need required. Debug and Windows. Debug Windows. So those are the these are what's launched. Cool. The subsystem manager is also responsible for creating environment variables, virtual memory, paging, files, and starts WinLog on service, the Windows logon manager. What is normal? So what's normal is that it starts from here. Its parent process is system. Number of instances, 1 master instance and child instance per session. The child instance exits after creating the session. User account, local system, and start time within seconds of boot time for the master instance. What is unusual? A different parent process other than system and PID4. The image path is different from Windows System 32. More than one running process. Children, self-termination, and exit after each new session. The running user is not the system user. Unexpected registry entries for subsystem. So that would mean that, like, if there's extra stuff here in the required field, that would be a bit sketchy. I'm pretty sure. So aside from csrss.exe, what process does smss.exe spawn? That was WinLogon.exe. Was correct. Great. I feel like we're learning something. All right, I think we're about half, or just a little bit under halfway. All right, so csrss.exe. As mentioned in the previous section, the client-server runtime process is the user mode side of the Windows subsystem. This process is always running and is critical to system operation. If this process is terminated by chance, it will result in system failure. This process is responsible for the Win32 console window and process thread creation and deletion. For each instance, csrsrv.dll base serve.dll and winserve.dll are loaded along with others. This process is also responsible for making the Windows API available to other processes, mapping drive letters and handling the Windows shutdown process. You can read more about this here. Note, recall that csrss.exe and winlogon are called from the subsystem manager at startup for session 1. So what is normal? So we have session 0 of this process. Normally image file name is here, command line, there's a bunch of stuff, current directory, Windows system 32, and parent, there's no parent. And non-existent process 488 there. Non-existent process, yep. Notice what is shown for the parent process for these processes. Remember, these processes are spawned by smsss, ssss.exe, which self-terminates itself, which is explains why this is non-existent. Even though there's a process ID, that's the one that started it, it's no longer existent, it's gone. So image path, system root, system 32, created by, so parent process created by an instance of smss.exe, number of instances, 2 or more, user account, local system, and start time within seconds of boot time for the first 2 instances for session 0 and 1. Start times for additional instances occur as new sessions are created, although only sessions 1 and 0 and 1 are often created. What is unusual? Well, an actual parent process, because the subsystem manager calls this process and self-terminates. Image file path other than Windows System 32, and a subtle misspelling to hide rogue processes masquerading as this process in plain sight, and the user is not the system user. What is the process which had the PID 384 and 488, which is what we saw here, and that is smss.exe. Cool. All right. WinInit. The Windows initialization process, or WinInit.exe, is responsible for launching services.exe, lsas.exe, and lsizo.exe within session 0. It is another critical Windows process that runs in the background along with its child processes. So let's have a quick look at that. Where are we? So we have WinInit, services, shut that, lsas, yep, that's what that looks like. Note, lsizo.exe is a process associated with credential guard and key guard. You will only see this process if credential guard is enabled. Time for a drink. What is normal? So, go back to general. We'll see that the image file path, and a lot of these are very similar. Windows System 32, WinInit.exe. It is created by an instance of SMSS which is here, non-existent process. Number of instances, there's just one. Local account, local system is the user account, and start time within seconds. What is unusual? An actual parent process. Because again, smss.exe calls this process and self-terminates. It's gone afterwards. Image file path other than the Windows System 32 file path, subtle misspellings to hide rogue processes in sight, plain sight, and multiple running instances and not running as system. Which process might you not see if carriage guard is not enabled? Elsizo.exe. Is that how you spell it? Yep. Easy. The next process is the Service Control Manager, SCM, or services.exe. Its primary responsibility is to handle system services, loading services, interacting with services, and starting and ending services. It maintains a database that can be queried using the Windows built-in utility sc.exe. Information regarding services is stored in the registry, which we can see at HKLM. System, current, control set, and services. And then there's a list of services there. This process also loads device drivers marked as auto start into memory. When a user logs into a machine successfully, this process is responsible for setting the value of the last known good config to that of the current control set. This process is the parent to several other key processes: SVC host, spools, spool SV, MSM, PENG, and DLL host, to name a few. You can read more about this process here. Another wiki page. What is normal for this? Well, let's have a look. Again, we see very similar things. We go into token, we see that it is in session 0. We also see that image file name is Windows System 32. And we have WinInit, which is its parent. Started around boot time. Again, number of instances 1, local system is the user account, within seconds of boot time is when it started, parent process is WinInit. What is unusual? A parent process other than WinInit, image file path other than System 32, and subtle misspellings to hide rogue processes inside, multiple running instances, and not running a system. How many instances? Should be 1. All right, so now we're going to look at the SVC host, which is service host. The service host process for Windows services is responsible for hosting and managing Windows services. The services running in this process are implemented as DLLs or dynamic link libraries. The DLL to implement is stored in the registry for the service under the parameters subkey in service DLL. The full path is this right here: HKLM system, current control set services, service name, which I'm guessing gets changed, and parameters. The example below is a service DLL value for decom launch service. To view this information from within Process Hacker, right-click Services Host. Process, in this case, it will be PID 748. Let's just have a look. right click it. We'll go to services, decom launch, and go to service. Right click the service and select properties. Put service DLL and it is rpcss.dll. Okay. From the above screenshot, the binary path is listed. Also note that how it is structured. There is a key identifier in the binary path. So that's this. This is how a legitimate SVC host process is called. The K parameter is for grouping similar services to share the same process. This concept was based on the OS design and implemented to reduce resource consumption. Starting from Windows 10 version 1703, services grouped into host processes changed. On machines running more than 3.5 gigabytes of memory, each service will run its own process. You can read more about this process here. Back to the key identifier -K from the binary path in the above screen. The -K value is decom service, decom launch. Let's see. Yeah, there. The services are running with the same binary path in the virtual machine attached to this room. Each will have a different value for service DLL. Let's take LSM as an example and expect the value for service DLL. So LSM. Too far. And we have LSM.dll. There we go. But it also started with decom launch. Since SVC hosts will always have multiple running processes on any Windows system, this process has been targeted for malicious use. Adversaries create malware to masquerade as this process and try to hide amongst the legitimate SVC host.exe processes. They can name the malware SVC host.exe or misspell it slightly, such as SCV host. By doing so, the intention is to go under the radar. Another tactic is to install/call a malicious DLL. There's an extra reading there if you want. So what is normal? Again, it's got to be running from system32. Its parent process is services.exe. There can be many instances running. The user account varies. It can be system, local, network service, local service, depending on the SVC host instance. In Windows 10, some instances run in as the logged in user. And that's true because I've seen that a lot in the investigations. Start time, typically within seconds. Other instances of SVC hosts can be started after boot. So what's unusual is if there's a parent process other than services, if the image path isn't system32, if there's any misspellings, and the absence of the K parameter, which is the normal way to start a binary. What single letter parameter should always be visible? K. So lsas.exe. Have a look at this one. Per Wikipedia, Local Security Authority Subsystem Service, or LSAS, is a process in Microsoft Windows operating systems that is responsible for enforcing the security policy on the system. It verifies users logged in onto a system, Windows computer or server, handles password changes, and creates access tokens. It also writes to the Windows security log. It creates security tokens for Security Account Manager or SAM, AD, Active Directory, and Net Logon. It uses authentication packages found in the LSA registry key. LSAS.exe is another process adversaries target. Common tools such as Mimikatz are used to dump credentials, or adversaries mimic this process to hide in plain sight. Again, they do this by either naming their malware by this process name or simply misspelling the malware slightly. And here's an article to see how LSAS is used maliciously. What is normal? Image path needs to be in system32. Its parent process is WinInit. Number of instances, there should only be one. User account is local system, and start time within seconds of boot time. It needs to have a parent process of WinInit. So if you see that it's not, then it's funky. It might be unusual. Image file path other than Windows System 32, subtle misspellings, multiple running instances, and not running as system. Those are things, signs of what is unusual. Now, WinInit in.exe is the parent process of LSAS. The Windows logon, WinLogon, is responsible for handling secure attention sequence. It is the Alt-Control-Delete key combination users press to enter their username and password. This process is also responsible for loading the user profile. It loads the user's ntuser.dat into HKCU, which is HKey something user, KU, CU. What is that? Have a look. Current user. HKCU is HKey current user. And user init loads the user's shell. Read more about this process here. It is also responsible for locking the screen and running the user's screensaver, among other functions. You can read more about this process here. Remember from earlier sections, smss.exe launches this process along with a copy of csrss.exe within session 1. So let's WinLogon. Can we find that? Oh, there you go. WinLogon. What is normal? The image path is system32. It's created by an instance of smss.exe that exits. So analysis tools usually do not provide the parent process name. There's one or more instances, local system user account, and start time within seconds of boot. Additional instances occur as new sessions are created, typically through remote desktop or fast user switching logons. What is unusual? An actual parent process. SMSS calls this process and self-terminates. Image file path other than system32, misspellings and not running a system, and shell value in the registry other than explorer.exe. So that would be local machine, software, Windows NT. Just having a look at this registry key. current version in WinLogon. No, that is not the thing I was looking at. Where are you? There it is. So we have shell here, and it is Explorer exe. Cool. What is the non-existent parent process WinLogon? We are at the final one. The last process we'll look at is Windows Explorer or Explorer.exe. This process gives the user access to their folders and files. It also provides functionalities for other features such as the start menu and taskbar. As mentioned previously, the WinLogon process runs user init, which launches the value of the key that we've just seen. User init.exe exits after spawning Explorer.exe. Because of this, parent process is non-existent. There will be many child processes for Explorer.exe. What is normal? Again, system root Explorer.exe. It's created by user init and exits. Number of instances, one or more per interactive logged in user. Logged in user is the user account, and sys start time first instance when the first interactive user logon sessions begin. What is unusual? An actual parent process. User init calls and this process and exits. An image file path other than C Windows. Running as an unknown user, subtle misspellings, and outbound TCP IP connections. The above image is the Explorer.exe properties view from Process Explorer. This one. So we'll go properties. Here, there are no TCP IP connections. Image. Again, normal. That's what it looks like in the command line. I never understood why they capitalized the exe, but sure. All right. What is the non-existent process for Explorer.exe? What is the non-existent process? User init. Yep. Understanding how the Windows operating system functions as a defender is vital. The Windows processes discussed in this room are core processes, and understanding how they usually operate can aid a defender in identifying unusual activity on the endpoint. With the introduction of Windows 10, no new processes have been added to the list of core processes to know and understand normal behavior. Earlier, it was mentioned that if Credential Guard is enabled on the endpoint, an additional process will be running, which will be a child process to wininit.exe. And that process is lsizo.exe. This process works with LSASS to enhance password protection on the endpoint. Other processes with Windows 10 are runtimebroker.exe, taskhostw.exe, formerly taskhost, and taskhostx. Please research these processes and any other processes you might be curious about to understand their purpose and their normal functionality. This information has been derived from multiple sources, which are these. Other links are provided throughout the room. Reading them at your own leisure to further your foundation and understanding the core processes is encouraged. The end. Nice. Well, I hope you learned a bit about Windows core processors. I know I did. Had a bit of fun with the registry keys. Had a bit of interesting time with understanding how to use a bit of Process Hacker and Process Explorer. And yeah, I just thought it was interesting learning about the user mode and kernel mode, those differences. But anyways, I hope you enjoyed this video, and thanks for joining me. If you're joining me live, I will see you in the next one, hopefully very soon. In the meantime, have a good day, good evening, good night. See you later.